So Happy New Year. Welcome to this webinar, which will be focused on domain testing. If you encounter any issues, I see a lot of people have already started writing in the chat, so feel free to use that. I'll tell you a few words about why we organized this webinar, and then I'll give it over to Cem. So we were inspired to organize this because we are preparing to start teaching along Cem Kaner the BBST Domain Testing course, which will be this month. But if you'd like to learn more or hear more about other techniques or topics related to the BBST courses, let us know what you're curious about. We're open to suggestions because we'd like to keep trying to address in one way or another, maybe through webinars, maybe other means, topics that we think can help us improve how we actually do testing. So coming back to the theme of this webinar, I think that the use of testing techniques is one important part in doing skill testing. So it's my pleasure to have Cem Kaner here, who will be presenting an overview of this testing technique, along with examples on how to use it. So if you have questions during the webinar that you'd like Cem to address, you can use the Q&A option in the bar at the bottom, and we'll make sure to address them during or at the end of his presentation. So with this said, I'm giving it over to Cem now. Hi, Cem.
Hi, Alexandra. Thanks for coming to this presentation on domain testing. For those of you who've seen presentations from me before, you've probably come to expect that my slides have too much text and carry more information than I'm going to actually speak during a webinar. As seems usual, even though I tried to work on it for this one, there's more text than we can possibly cover. So the slides are there to a large degree for reference. Domain testing is a software testing technique. It's probably the most widely taught, maybe the most widely used. Like all software testing techniques, domain testing teaches you a way of thinking about how to design tests. In domain testing's case, when you boil it down, it's really a risk-based test technique. It provides a sampling strategy for variables to help you efficiently hunt for bugs that are associated with how the program handles its data. And domain testing is a funny name for this technique. People have called this by a variety of other names, like equivalence, class analysis, boundary case analysis. But where the name domain testing comes is from the definitions of mathematical functions. So here we have this function, f of x and y, which just sets x to be a percentage of y. So if x is 1 and y is 2, then the function says it's 50. Notice also there's a third variable here, z, which is the value of f of x, y. So we have 3 variables in the definition of this function. Now the domains of this function, we have an input domain, which is the set of all possible values of the inputs of the possible values of x and the possible values of y. And then we have the output domain, which is the set of possible values of the outputs, the set of possible values of z. Domain has a different meaning entirely for many people. Domain often refers to subject matter. So for example, if you were dealing with an accounting program, the subject matter of that program is accounting, and an accountant who works with the development of the program would typically be called either a subject matter expert or a domain expert. And so it seems pretty obvious to many people to say that domain testing probably refers to testing that's done by a domain expert. There's nothing wrong with that usage except that it's not the most common usage in software testing. In the history of software testing, the term domain testing typically refers to mathematical domains, function domains, rather than to subject matter domains. And that's what we're going to talk about today. So here we are back to this mathematical function that defines an input domain and an output domain. But in mathematics, we have a luxury. We can leave all sorts of values of the variables undefined. So here, if y is 0, or if x or y are negative, or if they're not integers, the function is just undefined. It doesn't do anything. And so we typically call values of x and y that are outside of the defined domain for the function invalid values. This is a luxury that mathematicians have. They can say, well, it works for these values and it doesn't work for the others, and just ignore them. But in programming, we can't do that. In programming, we have to write our programs to respond appropriately to every value that the program could possibly see, period. If the program can see it, it has to cope with it. Unlike mathematics, where if the function doesn't like it, it can just turn its head. So in mathematics, if we give, the function f of x, y a value of 1 for x and a value of 2 for y, it responds with 50. X is 50% of y, and our programmed function should respond with 52. But on the other hand, if we give our function under test a value of -1 for x, the mathematical function says you can't do that. The programmed function has to actually say you can't do that. It has to respond to invalid values with proper error handling. So when we test programs, we have to allow for the fact that people accidentally make mistakes typing, that people have cats that jump up on their keyboard and do whatever they do, and now you have crazy input values. The program has to cope with anything that can possibly be fed to it. So when we test programs, along with handling the values for which the function is defined, we have to allow for the possibility that a value will come into a function that is too big or too small or too strange. And there's an infinite number of values that we could imagine, so we don't really want to plan to test them all because we can't. So we have to develop a sampling strategy that lets us test just a few values, but is intelligently enough constructed that will probably catch most of the bugs that we could catch if we tested everything. And that's what domain testing is for. In programming, another difference between that and mathematics is that we define data types. In mathematics, it's enough to say x is an integer. In programming, along with saying x is an integer, we say what kind of integer, because the programming language has to reserve space. How much space in the computer's memory are we going to allow for this variable? And so I'm going to say that these variables are short integers. A short integer in Java can take any value between -32,768 and +32,767. So when we're testing a program that implements this function, the valid values of x run from 0 to 32,767. A short integer could have negative values, but this function is not defined for negative values. The valid values of y run from 1 to 32,767, and all the other values are invalid. If we think just about the variable x, we can imagine a set that runs from 0 to 32,767 and includes only integers. That set's called an equivalence class. The definition of an equivalence class is a set of values that we think, it's subjective, a set of values that we think the program will handle in the same way. Different people can look at the same program and divide its possible values into different collections of equivalence classes. Different reasonable people can make different judgments and come up with different equivalence classes for the same variable in the same program. There's nothing wrong with that. Here are some of the equivalence classes that would be typical for the variable x. We have the valid values that range from 0 to 32,767, and then we think of the values that are too small, And I'm going to start with the ones that are the short integers. So those range from minus 32,768 to minus 1. But then we have other values that are too small that are not short integers. Anything that's less than minus 32,768. You shouldn't be able to stuff a value less than minus 32,768 into the variable z. It should be impossible. But that doesn't mean that the program couldn't try and fail. Then we have values that are too big. But anything bigger than 32,767 is not a short integer. And then we have the other values that you can imagine, but that aren't short integers or long integers or integers of any kind, like letters and operators, plus signs, minus signs, that kind of thing, and other kinds of non-numeric characters, or floating point numbers, or expressions like 3 minus 2 that will end up giving us a short integer, but that are not themselves short integers. So we could test from each of those sets. There are a lot of possible values. We don't want to test all of them. Let's look just at the simple number cases first. We have all the possible integers from minus infinity to plus infinity. That's a lot to test. I want to show that with equivalence classes, we could break that down to 6 tests. We start out with the values that range from 0 to 32,767, and just test at the boundaries, 0 and 32,767. The idea here is that if it's going to fail with a valid value, it's as likely to fail with 0 or 32,767 as with anything else. And maybe at the extremes, it'll get confused. Somebody will have written an inequality incorrectly and refuse to parse 0 or refuse to process 32,767 when you input it. So if we test with those two values, we're testing the general case. The program can't handle valid input at all, as well as the specific risk cases. Maybe it has a problem with the extremes. Similarly, with the extreme or with the negative values, these are invalid. We test at the boundary, -1, and we test it at the other boundary, minus 32,768. Probably if it doesn't have trouble with -1, it won't have trouble with the other one either. But if we're going to test all the boundaries, we would include that too. The next interesting one to test is any value less than minus 32,768. When I hear any value less, I look for a boundary minus 32,769. And similarly with bigger than 32,767, we have plus 32,768. These values are interesting again because they're not short integers. They're outside of the data type that the program should be able to cope with. But they're the values that are the most like short integers. They're almost short integers. So if something's going to get confused and try to process values that are not short integers, it's probably going to try to process these. With 6 values, we're dealing with a very small proportion of the total set of values that are available to test. That said, if we just think of the valid values, there are 32,000 of them. And if we think of the invalid values, it's an infinite number, and we're testing 6. With those 6, we're probably going to learn almost everything that we could learn if we actually tested every possible value. Now, if we go outside of the simple numeric case, we end up with equivalence classes that don't necessarily have obvious, easy boundaries. We can end up with characters that are not numbers and not operators. What's the boundary of the set of letters or the boundary of the set of Unicode characters? We can try to construct boundaries on those, or we can look at special case values that are likely to be troublesome, whether we can put them in an ordering from smallest to largest or not. So for example, look at the Unicode character 00B2. This is a superscript 2. If you have an expression like x squared, the little 2 beside the x is this little 2. Now, is that a 2 or is it not a 2? Looks like a 2. Maybe a programmer could look at that 2 and say, yeah, that's a 2. But this 2 is not the same as the 2 that you have that runs 0, 1, 2, 3, 4, 5. So if the program accepts this 2 as a 2, There might be some functions that go crazy when they try to parse something whose ASCII code is 00B2. I don't know how the program would handle this, but that makes it interesting to respond to. In general, we're not looking at boundaries anymore, but we are looking at what are called best representatives. A best representative of an equivalence class is either a boundary value or it's some other value in the class that seems in some way more likely than other values in the class to cause the program to get confused or to fail. And I suspect that superscript 2 is more likely to give some programs trouble than an A or a B. So the sampling strategy for non-numeric inputs is harder. We have to think more about what value we use, but the principle is the same. We have an equivalence class, a set of possible values that we're interested in testing. We sure don't want to test them all. So we pick a very small number of best representatives to represent the full set. And we're picking best representatives because we're looking for those few that if any are going to cause the program to fail, these ones are the ones that are going to cause the program to fail. This technique is entirely focused on data. This is one of the limitations of domain testing. It's there to help you decide which values of a variable to test. It's not going to tell you how to run the test. It's not going to tell you how to decide whether the program passed the test or failed the test. There are a lot of ways the program can fail other than crashing. So if you're looking for data corruption, for example, you have to look at something to see if the values are correct or if the screen is giving you something bad. This technique doesn't tell you where to look. It just tells you that if you're going to run a test, -2 is an interesting value to include. Like every other test technique that I can think of, this technique is guiding you in a portion of the task of test design, but it doesn't give you the entire design of the test. Because of this, quite often when we design tests, we end up with tests that are a combination. They end up being a mixture. We use domain testing for the variables, and we use some other technique for some other aspect of the test. I'll come back to that at the end of the lecture. Let me give you a working example instead of these pure mathematical functions. Here's a company called cars.com that will sell you cars over the internet. So unless you have lots of cash, you're going to take a loan to buy a car. And so cars.com helps you figure out how much the monthly payment is going to be if you buy a car from them. So here's its loan calculator screen. It gives you 6 input variables: the price of the vehicle, the down payment, how much you get for the car you're selling them, how much the sales tax is, what the interest rate is, how long you're going to take to pay out the loan. And then we have 2 output variables. It displays the price of the car and it displays the payment per month, which is probably what you're using this calculator to find out. So we can enter a car that has a $20,000 price tag and a payment of $5,000 is the first payment you make. We sell them a car for $3,000. The state charges a 10% sales tax. You pay the company 4% for the loan, and you take the loan for 84 months, and poof, it's going to cost you $191 a month. The car price is displayed as well. It's $20,000. You said it's $20,000. They say it's $20,000. But the main thing you're asking is, how much is this going to cost me? $191 a month. So here we have different kinds of values into this calculator. We have the input values. And for the 6 input values, like the price of the car, what are their boundaries? What's the biggest input value? What's the smallest input value? How expensive a car could this calculator let you buy? What numeric values will the program reject? Can you really buy a $20 billion car? Will it let you calculate the cost of that per month? What does it do if you try to enter non-numeric values? And does it treat all of the different types of non-numeric values the same? These questions are the traditional questions that domain testers were asking, say back in 1979. when this technique was really being published as an exciting new technique. But we also have the result values. Are the calculations of estimated payments correct? The program tells you that you're going to pay $191 a month. Is it right? The other question that we have, what are the biggest and the smallest estimated payments that this program can handle? Can you actually get a situation where the program will calculate out that you have to pay $20 billion a month? I don't know. If the program, for example, is trying to give you a small, a short integer as the output, then the largest possible loan payment you could pay is $32,767 a month. There aren't many cars that are going to require you to pay more than that. So maybe they restricted their values to that. But what happens if you set the input values so that it's going to end up trying to calculate a loan payment that is bigger than the largest loan payment it can store? What's this program going to do? That's the domain testing question. How do we force an output variable to get a value that is bigger than it can show? How do we get a result value to have a value that is bigger than it can store? And so with output values, these are the values you see on the screen. Can you set a price that's too big to display? Can you calculate a payment that's too big to display? Will the program save these values or mail them to someone? Is it going to save them to a disk file? Are there any values that are going to be hard to save? The final question with domain testing, how many tests are you going to have to run to check this thing? The idea with domain testing is that it gives you a planning structure to figure out a small number of tests you can run, and you just run those instead of running a bunch of other tests that are similar to these, but that really give you no added information. And that takes us to 1979. 1979, Glenn Myers published his famous book that explained how to do input validation checking using boundary class and equivalence class analysis. It was very exciting back then. Many people worked with Myers' work and extended it after that. I took my hand at it, but it wasn't until 2010, 2013, that Padmanabhan and Hoffman and I gathered individual blog posts and our own work that had tried to take specific cases of systematically looking at invalid inputs and saying, well, what's the theory for processing invalid inputs? How do we systematically go through with this impossibly large set of possible values and sample from it in the domain testing way? For valid values, everybody understands. But for invalid values that are not just too big or too small, what do you do with those systematically to cover all the interesting cases, but not spend an infinite amount of time on them? So that's one thing we covered. But this is still looking at the early approach, the 1970s approach, which applies only to numeric variables. It focuses only on individual variables. We're testing one variable at a time. And really it boils down to asking two questions. Is the program properly protected from bad input? And does the program properly handle acceptable input? Over the next 30 years, people generalized this in many ways. But I'm going to stop for a second and ask, is there anything that's been coming through on the question or comment list that I need to address before I go on? Alexandra, your mic is muted. Do you have anything that I should know about?
No, so far so good.
Okay, I'll keep talking. The first way that people generalized was in the academic world. University professors started dealing with the question, how can we use domain testing for multiple variables? It was in fact when they dealt with multiple variables and crazy geometric shapes for sets of input variables that we're looking at together that they stopped trying to talk about equivalence classes and boundaries and said, look, there are domains of functions that are multidimensional domains. So for example, Well, actually, the first case is the easy case. I'll do my for example in a minute. But the easy case for handling combinations of variables happens when all of our variables are independent. Here, for example, we have a function of a, b, c, d, e, and f. And a variable like a is independent of all the other variables if the value of a does not limit the values that the other variables can take. And if none of the other values of any of the other inputs limit the values of a. We know how to do that kind of testing. We generally use combinatorial testing. You might be familiar with a subset of combinatorial testing called all pairs testing. And so that gives you an efficient way of testing a bunch of independent variables together. What domain testing adds to this is that for each variable, it helps you pick a small number of values for A, a small number of values for B, and so forth, so that the number of combination tests doesn't explode to be this crazy set that you can't handle. But the analysis for the individuals is the individual variables is straightforward. And there are plenty of programs. Once you have a set of values for A that you want to test and a set of values for B and so forth, there are lots of all pairs testing programs that you can use to design the full set of tests. The program we looked at, cars.com, we could probably use combinatorial testing for. There is one set of interdependence. It's hard to imagine a down payment that is greater than the vehicle price. So in theory, vehicle price should constrain down payment. But actually, if you look at what happens with the program, it accepts this and basically says, look, if you're going to pay down, if you're going to give a down payment that's more than the vehicle price, there's no loan involved, so the loan value is 0. And so even though it doesn't make sense to give a down payment greater than the vehicle price, unless you're doing money laundering, but even though it doesn't make any sense to give a down payment that's greater than the vehicle price, the program will accept it. It's just an extreme value that the program works with. So we could test the program with these 6 variables using all pairs testing and achieve all of the kinds of combination tests that we might find interesting. Here's the hard situation. Suppose that we have 2 variables that limit the values of each other. For example, suppose that we're going to have a function that's just defined on a set of variables where x squared plus y squared has to be less than 25. This defines a circle. So here, the input set is a circle where the function is going to be x plus y. But anything that's not inside the circle, any values of x and y that are not inside the circle, we're going to call them invalid. So great. X is 0, y is 5 is a fine input value. X is 0, y is minus 5 is a fine pair of input values. But x is 5, y is 5, that's not acceptable because that's going to give us x squared 25 plus y squared 25 is 50. So the corner case, the case where we have the extremes of both variables, is not inside the valid domain, even though the extremes of each individual variable are inside the domain. And so mathematicians did this and said, how do you test a function that does that? Take your domain testing and deal with it. Well, you can deal with it, but what you're going to have to do is to have a pretty deep knowledge of the relationships among the variables. And so the computer science papers, you had all this big publication of lots of computer science papers that said, look at this input domain. How are you going to design tests for that? They had a lot of fun with it. People got PhDs. It was great. In terms of explaining how to deal with this to humans, to people who are not mathematicians and whose life is not focused around mathematics and who aren't trying to test programs that are written for people whose life is focused around mathematics, there have been several attempts to take that work and explain it to everybody else. I think the best 3 were written by Boris Beiser, who took the academic work and explained it as well as he could, to Paul Jorgensen, who said, yeah, the mathematics is great, but let's look at real life cases of constrained variables. For example, if you think of dates, February 30th is not okay, but January 30th is. So sometimes we run into real life cases where we have variables that limit the values of each other. How do you do the analysis for those, for cases where it's meaningful? And then in the domain testing workbook, we tried to collect everything and give examples that could give you kind of the general analysis. All three of these try to make everything understandable for non-mathematicians, and to some degree they succeed. It's imperfect. So this is a challenging situation. We're still dealing with inputs, just more complex sets of inputs. But you know, when somebody goes to cars.com and tries to figure out how much they're going to pay, it's nice that you can enter values into the inputs. But the only reason you're spending all that time entering the values into the inputs is to find out what your monthly payment is going to be. That's the reason to have the program. The input values don't matter if the output value isn't right. And so rather than staying in 1979 and asking, can we protect the program from bad inputs? We move forward a little bit and say, yeah, but does it actually give you the numbers that you need? Let me come back to vocabulary. In f of x and y are the input variables. Z is a result variable. It's the result of the calculation. When the program displays a value of x or of y or of z, when it prints it, when it saves it, sends it to another device or another program, that variable is an output variable. So x can be both an input variable and an output variable at the same time. It's an input because we're giving it to the function, and it's an output because we're displaying the value. Estimated payment, Z, is both a result variable. It was calculated to be $191 a month, and it's an output variable because it's displayed on the screen. When I started commercial testing, I left university, I went to Silicon Valley, and I started testing in software companies. Here we are dealing with database programs and creating spreadsheet programs. People are using our programs to do calculations. And so we understood right away that we weren't just using domain testing to do input testing. We were stretching people's descriptions to do calculation testing, to check our result variables and to check whether we were outputting values on the screen in a way that people would understand, and to check whether it was saving the data to disk appropriately. Now, all around us in Silicon Valley, people were doing the same kind of thing. They're saying, how do I create values that will create boundaries for the calculations instead of just creating boundaries for the inputs? And how do I do that in a way that manages the efficiency of our test suites so that we aren't testing an infinite number of inputs just to do thorough testing of the calculations? The books weren't keeping up with us, and the academic papers weren't keeping up with us. They're too busy with x squared plus y squared. But in practice, this was the challenge in the 1980s that people were wrestling with. How do we check our calculations in an efficient way? Can we come up with equivalence class analysis and boundary analysis where we're forcing boundary values onto the result variables or forcing values onto the output variables that are boundary values? What inputs do we have to give to force boundaries on these other variables? As we thought about that, we realized what we were doing was risk-based testing. So let me come back to a type of risk-based testing that's focused on variables. But let me come back to what risk-based testing is in general. In risk-based testing, you're going to imagine a way that the program could fail. And then you're going to design a set of tests that try to force the program to fail in the way you just imagined. Maybe you can make the program fail that way, maybe you can't. But that's the structure of risk-based testing. Imagine a way it can fail, then try to make it fail that way. When you look at domain testing through a risk-based lens, you're taking a task and you're saying, this task involves data. It involves variables. What values of the variables might make this task fail? If you can imagine that the variables could contribute to a failure, then what are the riskiest values of those variables? The ones most likely to make the task have that failure. Those are the best representatives. So we imagine a possible failure. We look for the variables that are involved potentially in that possible failure. And then we create equivalence classes and best representatives targeted around the question, which values are most effective? If there's going to be a failure here, which values will be the most effective in producing that failure? What's the smallest set of values we can use that will either tell us, yeah, this failure can happen, or we're wasting our time, let's go beat up the program in some other way. Input filter testing, the traditional boundary and equivalence class analysis testing, involves a very simple risk analysis. The input filter is the set of code that protects the program from values that are too big, too small, or too strange, and allows the good values through. So an input filter is bad if it allows the programs to accept bad values. How do you test the input filter? You test with bad values. You look for values that are too small or too big or too strange, and we know how to use domain analysis to do that. We create equivalence classes and sample from those classes. The input filter is also bad if it rejects values that are not too small and not too big and not too strange, if it rejects values that are supposed to get through. So we create equivalence classes of the sets of values that should get through, and we sample from those. That's all that simple boundary and equivalence class analysis does from a risk-based perspective. But as soon as we get to result variables and output variables, we have a lot more risks. Here's some simple ones. We define a function, z equals x plus y, to have short integer variables. But now we can have an overflow risk. Even though we can keep x and y as valid values, suppose that we give x 32,767 and we give y 32,767. The input filter says, yeah, that's fine. But then we add them up and we try to stuff it in z, and it says, hey, the biggest number I can hold is 32,767. What are you giving me? And so the program fails with an overflow. We could do the same thing by trying to make z have minus 32,769 or any other value smaller than that. We're going to end up with valid inputs, but an invalid result. Suppose that we try to display the value of z. There's only so much space on the screen we're going to allow for that. Suppose that we mistakenly look at this and we say, yeah, 32,767, that's 1, 2, 3, 4, 5 characters. So we'll leave space for 5 characters on the screen. And then we try to give it minus 32,767, which is 6 characters. How does the program display that? Does it put stars across the screen to say, I can't display this? Excel does that, that's nice. It doesn't get the number there, but at least it tells you there's a number here that's too big. I can't display it for you. So that's error handling. But other programs might, crash or corrupt the screen. Paste minus 32,767 into a place that infringes on the space used for something else. Similarly, if you tried to save this on the disk and we allowed minus 32,767 to infringe on the space reserved for some other value, we're having what's called a buffer overflow, or the equivalent of buffer overflow. We've got a data overflow. We're going to corrupt the storage that's reserved for some other variable. So those are just a couple of examples of the many kinds of risks that we can have associated with result variables and output variables. There are lots of other things we can think of, but the first place in a risk analysis that we have to start by thinking is, here's this variable that we started with, nice variable. Where's the program use this variable? Where? So a variable came in. What functions of the program use the variable? Somebody's going to use the variable, otherwise we couldn't collect it. We wouldn't bother to collect it. So what functions are going to use it? There's maybe not just one, maybe there are many. And once we've got the variable in, where does the program display values of that variable, print them, save them, send them? And if we're getting values in, does it just get the values from a human or from a cat, from the keyboard? Or is it going to stored data? Or is it going to some other program to get the data? And what crazy things could these do? A file on disk or input from some other program, maybe a hacker. What crazy values could we get from there? So where is this variable showing up? Now let's take a pair. We have the variable and we have this theory of where the variable is showing up, where it's coming from or where it's being used. And then we say, okay, so how could it get into trouble? There are lots of ways it could get into trouble. Maybe we're going to use this variable in calculations. Maybe we're going to use this variable in a way that constrains the values of other variables. Like, for example, if you have a $20,000 car, you're not going to make a down payment of $40,000. So the $20,000 constrains the amount of the down payment. Are there other variables that should constrain this one? Can we set this in a way that breaks those constraints? Some variables have control over what the program does next, the execution path. So if the value of this variable is negative, we do this. And if the value is positive, we do that. Does the program actually go to the right place if we give it boundary values of different kinds? The other kind of thing that programs can do, or that variables can cause programs to do, imagine we have a variable that says how many things a program is supposed to process. Here, let's take input from 1 million people. How long could that take? If the program controls if a variable controls how much of something a program is going to do, then the variable is controlling how long the program is going to do it. If we make the program take too long or too short, is there any other part of the program that's going to be surprised because it's being asked to do something too soon? Or some other part of the program that's going to get grumpy and tired because it's sick of waiting for the program to get done this task and pay attention to it? So maybe we're going to have race conditions coming as a result of the size of this variable. That's another boundary too. Too long or too short instead of too big or too small. And there are a bunch of other ways that the program might use the variable's value. And any way that the program might use the variable's value is an opportunity for the program to get into trouble, which means it's an opportunity for testers to have fun. But we don't want to test with all of the possible values of the variables for each of these ways, because we have this variable with all of its values and these different ways that we could get values into the variable, and these different ways that the program could use the variable, and the different ways that the program could use the variable and get into trouble. That's too many ways for too many values. So how do we cut that down to not too many ways with not too many values? And that's what domain testing is all about. So the risk analysis here says, okay, if the program is trying to do this task, how could the values of the variables it's using cause it to fail? That's the risk question. And then we have the domain question. How can we bring the number of values of these variables down to something reasonable? What are the highest risk values of the variables so that we can just test with those? What's the set of values that could cause the failure? What's the best representative of that set? And let's run the test with that best representative. Now remember a best representative, because that's vocabulary many of you don't know or aren't used to. The best representative is like a boundary. Many times it is a boundary. But if you're dealing with a variable that doesn't have boundaries, it's some special case that seems more likely than the other values to cause the program to fail. We have to pick something to represent the set. If there's something that's a little more likely to cause the program to fail than something else, that's a better representative of the set. So we use domain testing for efficiency. We don't want to test with all those values because there are too many. And for power, we want to choose values that are more likely to give this program a dummy ache. So the scope of domain testing. It's usually taught as something that's focused on input variables. Input variables used to be very important in the 1970s. They're still important, but today we have programming languages that define data variables with strong typing, and all sorts of the bad inputs that used to be problematic before are just impossible to get into the program now. The language doesn't allow it. We have all sorts of programmers' libraries that apply input filters as well, let the programmer apply input filters. And so anybody who's gone past first year programming in courses, anybody who's actually studied the language they're working in, has lots of tools to make sure that their input is properly filtered. And so to a large degree, simple input value testing isn't really very interesting. And it is for the programmers who are writing the original code. But unless you're dealing with slobs as a black box tester, they've already done that. And so in modern testing at the black box, yeah, we do a little bit of input domain testing just in case, because, you know, not every programmer is really very careful. But probably what we find is that every programmer on the professional team is careful enough. And at that point, input domain testing isn't of much interest. Not much risk here. You want to make the program up in some way that's more likely to make it sick. On the other hand, there are no simple tools for making sure that result variables calculate their calculations correctly, or that output variables can actually save the data in the correct ways in the correct places. If we had automatic handling of that, we'd never have any buffer overflow bugs and we wouldn't have any security problems. So the handling of data past the input filter is where we really need to think about, and where things get very complex, and where domain testing can at least simplify part of the test analysis by helping us figure out what small set of values can give us as much help for testing against a risk as we can get from thinking about the variables. So the application of domain testing in modern black box testing is, to some degree, the textbook application. Let's beat up the input filters. That's simple and fun. It can keep us looking busy. But most often, when we're dealing with seasoned programmers who are reasonably careful, the way you're using domain testing is in combination with some other test technique. The other technique has given you an idea for a test, but it doesn't necessarily tell you what test variable values to use. It gives you insight into some other aspect of the test. And now you say, okay, so what do I set my variables to as I'm doing this other test? And you look at domain testing and say, what's the smallest set of variables? If I'm going to do this test with these variables, how many times do I have to do this test? With how many values of the variables? Not many, I hope. And I'd like to choose the most powerful values of the variable. so that if I do run this test a few times with different variable values, I'm running it in the few times that are going to make the program most likely to fail. So that at the end of running a few instances of this test, I can stop and say, yeah, I've done everything I want to do with this test. Let's go hunt for something else. So that's where I think domain testing is at its most important and most useful today. We use it all the time, but we use it as an enhancement to almost all of the other test techniques to add to their power and to increase their efficiency. That's the end of my slides. You guys probably have by now some comments or questions.
Yes, so I'm going to read the questions we have so far. One of them says, it's getting harder to understand the basic differences between domain testing and boundary values. So the question is if you could give a couple of basic differences between them.
Boundary value analysis is part of domain testing. In domain testing, you're always looking for equivalence classes, and you're always looking for best representatives for the equivalence classes. If the equivalence classes are numeric, if you can have values in the equivalence class that run from a small number to a large number, you can use boundary values. If they're not numeric, good luck figuring out boundaries, but you can still sample from the class. Where domain testing is broader than simple equivalence class and boundary analysis is that we apply this way of thinking when we're dealing with multiple variables, not just one, and when we're dealing with calculated values or output values, rather than thinking about equivalent inputs and boundaries on the inputs.
Okay, I think that addresses the question. Another question says, the old domain-based testing had the claim of being a methodical way to get a good enough coverage with respect to the equivalence classes we identified and assuming we identified them properly. When moving to risk-based perspective, aren't we ditching this claim and just saying we are doing the best guesswork we can, which, to be honest, is what is happening with equivalence classes implicitly, but here we don't even try to be methodic about it.
Oh, you can try to be methodic about it. Let me start first with the claim. We can claim that we're systematic and methodological and fully reproducible and professional and all those other nice words about anything. But you know, we're not. Risks are subjective. Equivalence classes are subjective. Quality is subjective. Bugs are subjective. Obviously, some bugs are obvious, and everybody in the world would agree that this is a failure. But all sorts of bugs are kind of, most people think it's a failure, and somebody says, no, it's a feature. It's subjective. And we can either accept that there's subjectivity in our field and cope with it, or we can walk around like little 3-year-olds and deny that the world is any bigger than what we can touch. So I've abandoned the notion of a methodology that gives me unambiguous everything for a long time. But methodologies can help us organize our thinking, even if they're not perfect, even if they're not mathematically certain. And the whole point of going through the development of the domain testing workbook, where Soumya Padmanabhan started out at the start of this project as an incoming master's student. And by the time we finished the book, she was senior engineer at Microsoft and then at Google. Doug Hoffman and I worked through how do we bring the methodology that we see in domain testing to kind of all corners of the problem. It took us 10 years. Did we come up with a perfect book? No, but we explain what we think the methodology is. We give a bunch of worked examples Some of them were very difficult. Some of them took us a long, long time to develop. But that's as good as it gets, at least as good as we could get it.
It's a great answer. Another attendee is asking, in what ways can domain testing be automated?
It can be automated in the same way that any other test can be automated. What do you have more in mind?
There aren't more details. Maybe you can, this attendee can post in the Q&A or the chat. In the meanwhile, there is one question which might be related to that, which says more towards lower level tests, but how does property-based testing techniques relate to domain testing as described here? And by property-based testing, he or she refers to testing a function's behavior rather than having specific inputs.
If you're dealing with a function, whether you like it or not, it has inputs. And the function behaves, but it does, it can behave correctly sometimes and not correctly other times. And to the extent that you're saying, are there any special circumstances under which I can make this function misbehave? You end up being able to imagine a set of circumstances under which you could try to make the function misbehave. And if your imagination is broad, you can imagine way too many details of those circumstances that would lead you to way too many tests to test them all. And so the question becomes, how do you sample? If you test a function, you're going to test it with some values. You can't just tell the program, run this function with no values. It might use default values, but you get to ask the interesting question. If you test, if a user uses it without the default values, with some other values, are there circumstances under which it will misbehave? To the extent that question is interesting, domain testing can help you answer it. To the extent that that question is not the question you're interested in today, domain testing isn't the technique that you're going to use.
We have another question about the output variables. How is an output variable different from a result variable? Isn't a result variable an output?
A result variable is an output if you're displaying it, if you're saving it, if you're printing it, if you're sending it to someone else. But if a function generates a result, then you might not be looking at that result. The program might not display it to you. The distinction is a conceptual distinction. The notion of the result variable is asking, as the function came up with some kind of calculation, is the result of that calculation the result that it should be? And the notion of the output value is, now that you're trying to display something, wherever it came from, might be an input, might be might be a result. As you're trying to display something or save something or sending it somewhere else, can it handle that aspect of dealing with the variable?
Another question is related to machine learning and AI. How can this be used in that area, in the machine learning or AI area? Do you have any thoughts on that?
I'm not an expert in that, but it seems to me that if I can imagine risks associated with machine learning, then as I try to figure out how to test for those risks, I'm going to end up thinking about using sets of data. And if I can think about using sets of data, I can think of some sets of data being more troublesome than other sets of data. And if I can imagine that, then I'm ending up with domain testing thinking. What's the most troublesome set of data that I can think of? Let's use that. To the extent that you can think that way, you're thinking along the lines of a domain tester. To the extent that that way of thinking is not useful, or not useful at this time, to help you explore the risks you're exploring at this time, domain testing isn't the right technique.
There is one more. There are two more questions. One is, how do you see domain testing used on products that are so complex that there are too many variables and combinations to test or even imagine?
There are always too many combinations to test. In general, when we're dealing with programs that have large number of variables that work in combination, we either use test techniques that are focused on testing massive numbers of variables in combination. The primary one is cause-effect graphing, which a small portion of the testing community knows how to use. It's often seen as a very, very difficult technique to use. And difficult to interpret because you might be testing 300 variables together at the same time. Or you test a smaller number of variables in combination. You end up listing your gazillion variables and saying, I think these would be interesting to test together. And you test 5 or 6 variables at a time, or fewer. And that choice of a smaller number comes when you say, well, I can think of this as a meaningful combination that would be interesting to test together. And I have a cognitive limit on how much I can do and how much I can interpret. But once you're in the cluster of testing 6 variables, you're either going to look at those and say, I think these are independent, and then you're going to use something like all pairs testing, or I think these are dependent, and then the world gets more complicated. Domain testing helps you a little bit by helping you reduce the number of values of variables you're going to test together, and helping you notice that as you think about the relationship with this other variable, the value of this one is a boundary when that variable has this value, but is not a boundary when the value of this variable has this other value. And that becomes complicated. It becomes time consuming. The only benefit to it is that the time-consuming analysis saves you the time of running massive numbers of tests that don't necessarily get you to the interesting test values if you were just sampling randomly. When things get complex enough, though, the reality is you're going to switch into random sampling. You'll grab some values that are obviously interesting tests, and those are going to come from a domain kind of thinking. But you're also going to generate lots and lots of tests that use random selections of values across as many variables as you choose to test. The challenge you're going to have in doing that automated random testing is figuring out how to identify whether the program passed or failed the test. If you can come up with an oracle, you can support very large automated testing of random combinations. If you can't come up with an oracle, if you actually have to sit a human down with a calculator and say, you figure out whether it's done the right thing or not, then you're going to have to do very careful thinking for the small number of tests that you have time to process, the time to figure out whether the program passed it or not.
Okay, so I think we can take a final question, and If there are more unanswered questions, we will try to address them via email afterwards. So this question is the following. Would it make sense to pick a random value from an equivalence class instead of sticking with one constant value, as you might not be familiar with what's inside the black box, so it may be hard to guess a best representative?
If you can't imagine a best representative, then you're doing random sampling anyway. If you're dealing with boundaries, there is some published scientific research that indicates that program failures are more likely at boundaries than at non-boundary values. From that, we generalize, and there's a little bit of research to the argument that any value you can look at and imagine a way in which it is more powerful than others gives it an edge. And when you have an edge, you have a slightly higher probability of finding a bug. Remember, you're not going to find a bug if the program doesn't have a bug. So you're just looking at the values that, that give you a chance to find something that may or may not be there. But if the program has that value or has that bug, if you have a theory of error that lets you think through what test values might be the most effective, that's going to generate best representatives. If you don't have a theory of error, boundary analysis is slightly more likely to give you best representatives, ones that are more powerful. And if you have no theory of error and no boundaries, then yeah, you're going to do random sampling.
Okay, we have, I think, another 4 questions that we will try to address in writing after the webinar,
Okay.
so that we don't go over the allocated time too much. So with this, I'd like to thank you, Cem, for the discussion as well as the overview and the insights you provided. And thank you everyone who came. We'll make the slides available right after the webinar will finish. And as I said, we'll try to address the remaining questions in writing. So thanks and have a great evening or start of the day, depending on where you are.